Next, let's discuss how to compute the backward probabilities. The backward probability is a function involving time t and I. So you can imagine that beta as a matrix is going to be n times mz. So for example, for this entry, it will correspond to the tth row. So this entry corresponds to the entry in this matrix, the tth row and ith column. Okay, so we're going to compute this beta matrix backward. First of all, if you look at the definition of beta t, because we only observe data the x till time n, so the maximum t value is only n minus 1. So we'll start with this. And I'll explain to you. You can actually think about the last row of beta just all equal to 1. Okay, so let's look at the calculation. The first calculation we need to do where t is equal to n minus 1. So we're trying to fill in the second last row. Okay, so beta subscript n minus 1 and I, and by definition, it is equal to the conditional probability of observing xn, the sample, conditioning on your previous latent state is I. So I draw the picture here. So we wanted to calculate this. How we calculate this one? Well, we make this probability to be a sum. We sum of the probability where we add the different value of the latent state at n. So this is a sum over z n equal to j. So now we're dealing with this graph. Okay. So for this probability, again, we play the same trick where it's just going to be the marginal of zn times the conditional of xn given zn. Of course, the original conditioning zn minus 1 is always behind the bar in each of the calculation. Okay, so we always conditioning on zn minus 1. But here you're going to find out the zn minus 1 becomes inactive because once we conditioning on zn, xn is independent of zn minus 1. And then those two probabilities are easy. We can directly grab it from our parameter space. This first probability is basically the transition probability from among the z's, and this is the emission probability. So we can compute beta at the t n minus 1 using some kind of product involving a and b. We don't need the last row, so let's just make this a trivial equality here. We're going to define the last row of beta to be all 1, so we can add a beta here, because you're going to find out in our later calculation, our calculation for beta t will depend on the beta from t plus 1. Let's continue with our calculation for the backward probability. As I mentioned before, you can think about the beta, the backward probabilities are arranged as a matrix n by m times m sub z. So we're going to fill in this matrix from the bottom. As I mentioned before, the bottom cells for beta will be all 1. Then we compute the row at n minus 1 and all the way up. Now suppose we have already calculated all the entries for the beta matrix till row t plus 1. Then let's talk about how to fill in the entries at the row t, which is the pink, is this row. Okay, so by definition, beta sub ti is equal to this. So that's the let me go to this graphic representation. So the beta sub ti is equal to this conditional probability. What is the probability of observing future samples at t plus 1 all the way to n, conditioning on your latent state at time t's I? Now this probability, we use the same trick, and we're going to add the latent state at t plus 1. So it's equal to sum over j of the same probability, but we now going to add the latent state at t plus 1 and to be j, and we sum over all possible value of j. And now this graphic representation just try to explain why it is difficult to compute this conditional probability. this is a graph. We're going to use the same principle we discussed before. When we try to construct a subgraph of original graph, we have to add edges among nodes. They could be connected through variables which are removed already. So for example, in this case, you're going to find out if we only look at the future observations after time t and also the current latent state zt, you're going to find out any pairs of those variables going to be dependent. This is a fully connected graph. So do any calculation for this graph will be difficult, and we cannot just simply grab some numbers from the parameter space. So the trick is add the latency at time t+1. So we're talking about this graph now. Again, we're still going to see a lot of dependence among the future observation with the latency zt+1, but at least we separate the dependence between zt and zt+1 is pretty simple. Once we're given zt+1, the latent state at t+1, and then zt is independent of all the other observations. It is true this distribution over those variables are still difficult to compute, but we computed before because from our beta, the backward probability. So let's take a look at the calculation. By definition, beta t is equal to this. So this is equal to summation over j. We add the latent variable at time t+1, and we sum over all possible value of this zt+1. And then we apply the chain rule. First is zt, condition t+1 condition zt, and then it's the xt+1 condition on all the previous variables, but you're going to find out zt is irrelevant now. And then all the future observation starting from t+1, conditional all the previous, and you're going to find out it's irrelevant to those things. So the summation, the beta t is equal to summation of a product of three terms, and this term is basically from the transition probability A, and the second term is from the emission probability matrix B, and the last one is complicated, but that's actually from the row of the beta matrix at row t+1, which we computed before. So using this formula, we can gradually fill in the row t of this beta matrix. We can continue doing this until we'll fill in the first row of the beta. So we finish the computation for the backward probability.